What I'd like to do with this video, this is a video I, in a sense, didn't plan on doing, but because I was, especially the first time I, computed this solution to that last problem from the, the previous video, I was, it took a bit of reasoning with some things that I wasn't just completely confident were correct. So I wanted to find some way of checking my answer. And so I decided to write a fairly elaborate, not anything wild, but a fairly serious script for checking my answers, right? So I basically wanted to write a program that would essentially simulate these combinatorial processes, and it would be able to generate all words, generate all permutations, generate all multisets, generate all kinds of things. And then I wanted to be able to sort of specify certain properties of those words or permutations or whatever they might be, so that I could count only the things satisfying a given property, allowing me to take a problem like this where, okay, we're looking for all possible election outcomes, and I would like to somehow describe no one candidate getting more than half the vote, run the simulation on some example numbers, and see that my answer makes sense. So anyway, long story short, this video is going to be all about showing you the program that I wrote for validating my answers to some of these problems, and I'm very happy to report that my answer to that problem came out correct. So not only am I very happy that I got the answer right, but also that my software is really working, it's doing what I wrote the software to do, which is a second victory. So I'm very pleased with all of that. Okay. Now, the first thing, okay, so here we go. I'm starting to describe the program. And the first part of the program, I wrote this in like a Jupyter notebook. It's not that big of a program. But in any case, the first way that I approached doing this was that I would basically, I mostly just kind of relied on SymPy. SymPy is this absolutely fantastic, can't sing its praises enough, module in Python that allows you to do symbolic manipulations of mathematical objects, and it has a bunch of combinatorial functions. And so I was mostly just relying on SymPy, right? So basically here, to generate all possible nk words, right? N the size of the alphabet and k the length of the word. I basically used the SymPy function variations with the, you can see right here exactly what I gave it for the arguments, and you can sort of look up the documentation of that function if you're interested in that. But before I go too much further, I'm describing all of this as my first solution. It is not ultimately what I am going to be using going forward to validate my answers. And here's why. When I run these functions, they always output a list of all of the possible permutations or combinations or whatever the case may be. And when I got to a point where I wanted to simulate a deck of cards for a future problem, 52 cards easily crashed the program, right? The memory ran out way too fast, right? So you can't just return all the answers. If you have, I don't even know if a supercomputer or, maybe some computers in existence could do that, but with a 52 card deck, if you simulate that here and try to output all possible 5-card hands or something like that, or maybe not 5-card hands, but all possible like rearrangements of the deck or something like that, it's so absolutely gigantic that it will guarantee to crash your computer if you try to, right? You'll just run out of memory. So anyway, so that's the problem that I ran into. And so what I did was I fixed that problem by basically, I'm probably not using the right word here, but I basically made my own generators, which is to say I don't return an entire list or object of all of the permutations, combinations, or whatever the case may be. Instead, I made it basically just give me the next one and then the next one and then the next one. I didn't risk exhausting the memory in my computer because at no particular moment do I have to have all of them. I can generate one, see what it is, maybe I'll print it, or who knows, maybe I'll just count it. Who knows what I'll do with it. But in any case, I generate an item, maybe I use it one way or another, and then I throw it away and generate the next one so that memory is never really at risk. So anyway, so I just wanted to show the early version of this because it is more readable and it's a simpler solution. And if you're not doing things that are too big, it's a kind of nice solution. So you can see the code here. If you want to take it and do whatever you want to do with it, feel free. One of the sort of possibly more interesting features of the code is this generate function. And the idea behind the generate function is that I want to return the list of only the elements that are satisfying a property that I specify. So the domain is, right, so when I say generate domain map property, let me tell you what each of those three things are. The domain is going to basically be the list of all of the combinations. So if I was generating all permutations, the domain would be all the permutations. If I were generating combinations, that's what it would be, and so on. If I were generating a Cartesian product, that would be the domain, right? And these would typically, in the way that I've designed it here, those would be like lists of number or lists of numbers or something like that to represent permutations of elements, right? Map would be an optional sort of thing. I mean, it has to be specified here in the program, but you could just like map everything to itself if you didn't really want to do any mapping. But basically the idea is the domain is like, any one permutation is basically a list of some numbers. What if you wanted that list of numbers to be explicitly associated with some other kind of object that more accurately, precisely represents the thing that's in the problem, right? So, if it were the election situation, right, we might represent that with multisets, but maybe rather than having like a number mapped to a number as multisets do, I might want to instead represent that as the name of some candidate paired with a number, something like that, right? Just something that better represents the object, right? Like whatever is in the particular problem. So the domain is like this sort of canonical representation of permutations or whatever. The map associates those to whatever you're something more descriptive of your real world thing that it's supposed to correspond to. And then the property is basically going to look at any one of the outputs of the map and decide if it's one of the things that you want to count or not. And so basically the return value of this function is the list of all things satisfying your property. So that's the generate function. Slightly interesting, perhaps. I don't know. Anyway. Then I tested it out. So you can see here that I'm testing out the function. It works well. Oh, right. This was basically me testing it out on the earlier problem about the probability of die roll summing to an even number. And so I just ran it on some inputs or something like that and confirmed that my answer was correct. Anyway, here I basically ran it again on the rectangle problem and confirmed that my answer to the rectangle problem was correct. So that's great. Here I ran it on the RS strings, right? So that was the one about R consonants, S vowels. And so yeah, I simulated that. That came out to the right answer, it seems. And what else? What else? Right, and I guess here I did in fact run it on the multiset problem, and so basically I sort of used a representation of multisets for precisely this problem, and here it's nice that I can actually print out the multisets, right? It's really one nice thing about this is that you really get to see the things that you're counting. So this is showing me candidate 1 getting 30 votes and everybody else getting none. The next multiset represents candidate 1 getting 29 votes, let's say the next one, candidate B or whatever, getting 1 vote and everybody else getting 0, and so on. And that's just really nice that you can sort of visually, I only printed out the first 10 because there were so many that it would eat up the buffer or whatever. I don't necessarily know the right word for that, but in any case, so I basically ran my simulation for the multiset problem, and I got confirmation that I did everything correctly. So that's wonderful, right? And here when I find the length of that output, that's giving me the answer to the problem. And then down here, I compute using the formula that I derived, right? So I am, in fact, I guess actually this is for the first part of the multiset problem. And I suppose, down here, I'm giving it the property that no person gets more, right? Everybody has less than or equal to 15 votes, right? And then I run it here, and I also compute the formula that I derived as my answer to the problem, and I see that the direct enumeration is here, my formula's answer is there, so I got it right. Well, I guess, I did ultimately choose to approach future problems in a different way, like I said, using something like a generator. But that's not in this file. I must have put it in a different file. So when it comes up, I will show that other file in another video. But this is kind of neat on its own. And this is how I validated my answers to these problems.